So,
Hello.
hello.
Hola, ¿qué tal?
So,
¿Por qué no habla?
you have the file of the seminar number 4, I hope. Last.
Yes, we have it.
So, uh, here you can find also the a kind of homework for you. Uh, it was for Eric, but I think if you do these exercises, you can also discuss them in our future seminars. So if you want, but I think it will be good for you also. What do you think about?
Yes, I think it sounds good.
So Eric, we will find a method to discuss all these exercises. Okay? I don't know. Maybe
No, yeah, it sounds good.
during the seminar, or maybe personally, if you want.
Yeah,
do you
I recently I bought the book that you showed me, and I plan to get some of the problems. I'll review them with you, and then we can start. I'll make for the
So,
student, and I'll just give it to them personally.
Eric, as for the first homework, I try to give you only the exercises we discussed during our seminars. You
Mhm.
see, then
Yeah.
we can discuss something more difficult, more difficult.
Of
But
course.
in future, if you want to work, so it's your turn. And then I'm ready to discuss all these exercises with you, either during the seminar or personally. I repeat, but so you see, you have to find a method to discuss this. Okay,
Yeah, yeah, perfect.
perfect. So, dear colleagues, uh, we continue our seminar, which is called Limits. So please find page number 18. Page number 18. Is it possible? Is it possible to find the page number 18?
Is it
It is.
is it the
Yes.
one called bounded sequence, correct?
No, not
No.
sequence.
Sim-
Limit of sequence. The limit of a sequence.
Ah, perfect. Yeah.
So seminar number 4,
Hmm.
page 18.
Yeah, I got it.
Good. You can see.
That binomial theorem, correct?
So here some limits to remember. Exercise number 7. Slide 1. You see?
Yeah, I found it. Uh, I'm not sure. I think everybody else found it too.
So
yes, I found it.
good. So now we will discuss a new example of a limit to remember. So it is given by the formula 3.7. So here we have a any real number, and we want to find the limit as n goes to infinity of a to the power n over n factorial. Do you know what's this factorial?
Is it
I think yeah.
the negative
So,
number?
so for you, I recall you that n factorial is a product of the natural numbers from 1 to n. For example, if you have 3 factorial, it will be 1 multiplied by 2 multiplied by 3. So it will be 6. 4 factorial is a product of 1, 2, 3, and 4, and so on. So if I take n factorial, then it will be the product 1, 2, 3, and so on up to n. Is clear?
Yes.
Yes, it's
Yes.
clear.
It's clear. Now, so we want to prove this relation, this equality, 3.7. So I don't know really. I have any real number. It can be positive or negative. So I take an absolute value of a to the power n over n factorial. And I rewrite this equality in the following way. Absolute value of a divided by 1 multiplied by absolute value of a over 2, and so on. Then we have absolute value of a over m plus m. You see, m plus 1. And then we have all the other terms up to absolute value of a over n. Then you see why we take this special term, absolute value of a over n plus 1, because a is fixed, so I can also find a natural m such that the absolute value of a is less than m plus 1. I think it is clear.
Yes,
It's clear.
clear.
Now, the product of the first m terms gives us absolute value of a to the power m over m factorial. Here we have the product of m copies of absolute value of m of a, and in the denominator we have the product of 1, 2, 3, so on up to m, so m factorial. What is important here? This quantity is a constant. It is really a constant because a is a constant, is a real constant. And m is also a constant. So we can regard this as a constant. Now, the remaining part is a, absolute value of a over m plus 1 to the power n minus m. So in this case, what do we have? We have that absolute value of A over m plus 1, I can denote it by Q. This Q is less than 1. You see, because we choose our m such that absolute value of A is less than m plus 1. Is it clear?
Yes, it's clear.
It's clear. So now I say that this product, a constant by this Q or this absolute value of A over m plus 1 to the power n minus m is less than epsilon. then, what do we know? From our exercise number 6, we know that u to the power n, if q is less than, if the absolute value of q is less than 1, then the limit will be 0. So we have to use, you see, the power in this case is more complicated, but no problems with, because we have already n, and n goes to infinity. So due to the definition of the limit, we have that the limit 3.7 is 0. Is it clear? Or you have some additional arguments here? So you see,
No, I understand. I don't have any questions about this.
You have some questions, Eric.
No, I'm good.
So you see here, if you want, I don't know. Do you know the theorem of two policemen?
Which theorem?
The theorem of two policemen, or the squeeze theorem.
It doesn't ring a bell right now. I'm not sure.
So the theorem.
I think we know it.
You think you know?
Yes,
it's very good. So the idea. Here I do not use the theorem, but it is very useful exactly in this case. You see the idea, if you have three sequences such that x sub n is less than or equals y sub n less than or equals z sub n, and x n and z n have the same limit, then your y sub n converges and have the same limit. You see here, in this inequality, if I forget about my epsilon, you see, on the left-hand side, I have 0. So my term, absolute value of a to the power n over n factorial is really greater than 0. And from the other hand, on the right-hand side, we have some sequence which converges to 0. So on the left-hand side, we have a constant sequence 0, 0, 0, 0, 0, which converges evidently to 0. And on the right-hand side, we also have a convergent sequence which converges to 0. So our statement 3.7 is given by this theorem of two policemen. I hope, but if you do not want to use this theorem, or if you do not know this result, then you can argue with the definition of your limit, because you know that the sequence absolute value of a divided by m plus 1 to the power n minus m goes to 0. You know this limit, so you have to write the definition of this limit, and then you can find your cutoff capital K of iron as in the definition. Is it clear?
Yes, it is clear.
It's clear. Very good. So now, as for the next limit, we make use of the so-called page 19. We make use of the so-called binomial theorem. Binomial theorem. So here in this slide, you can see the formulation of the theorem. So if I have any A and B real numbers and any n natural number, then a plus b to the power n is given by the sum from 0 to n, some coefficients. The coefficients are usually called the binomial coefficient, Cnm multiplied by a to the power n minus m multiplied by b to the power m. The definition of these coefficients are given in the formula 3.9. So Cnm, capital Cnm, is n factorial divided by m factorial n minus m factorial. Here you see for you the definition of k factorial. It's the product of 1 to 3 so on k. And what you have to know also by the definition, 0 factorial is 1. It is done for the sake of simplicity. For the sake of simplicity. You see? Then what we will use in our exercises, it's the formula 3.10. So if I take a equals 1, then my formula 3.8 is simplified, and I have the formula 3.10. Okay? As you turn your page 20, for you, it is, I think you have to know all this from your lectures. But I recall you, the properties of my coefficient C, capital C and M. So if I take Cn0 or Cnn, I will have 1. The second property is Cnm is exactly Cn n minus m. And the last property, which is known as, I think, I'm not sure, but I think it is Pascal property. So the sum of the coefficient C and m plus Cn m minus 1 is Cn plus 1 m. So the formula, it is the third formula in 3.11. As for the first two formulas in 3.11, it is exactly by the definition of these coefficients. So I hope there is no problem. Finally, let's consider the third property in 3.11. I write the sum Cn plus Cn minus 1. So the first term is given by the definition, and the second one is also given by the definition. So I rewrite my sum as a product n factorial over n minus 1 factorial multiplied by n minus m factorial. You see here, m is a fixed number and n is greater than m. So we have that the first term is multiplied by the square brackets, and in these brackets we have 1 over m plus 1 over m plus 1 minus m. So we go to the common denominator in order to have that we have in fact the product n factorial over m minus 1 factorial n minus m factorial multiplied by a fraction n plus 1 over m multiplied by m plus 1 minus m. Then we have that m factorial multiplied by m plus 1 is exactly m plus 1 factorial. And in the denominator, we have m factorial multiplied by m plus 1 minus m factorial. And by the definition, it will be the coefficient capital C n plus 1 m. Is it clear?
Yes, it's clear.
It's clear. Very good. So we turn the page and let's discuss the exercise number 10. So one more limit to remember. So the formulation of this exercise is as follows. If I have a real number which is strictly greater than 1, then the limit as n goes to infinity of n to the power k, where k is a positive real number, then over a to the power n is 0. You see why I want to say that k is a positive real number, because if it is negative, even if here in the proof I do not precise that k is positive, but if k is negative, so I will have 1 over n over absolute value of k multiplied by a to the power n, and this fraction has a limit 0 always, because it is 1 over infinity if you want. So here I can say that my k is a positive number. then I can find an integer, or in this case, it's better to say a natural number m, such that m is greater than or equals k. Then I have an evident inequality, n to the power k over a to the power n is less than or equals n to the power m over a to the power n. Then you see, I want to use some new notation. So I introduce a constant, which is mth root of a, and I denote this mth root by the letter b. Then I will have that I want to estimate, I want to use my ideas about the limit to the sequence n over b to the power n and all this to the power m. You see.
Yes, I see it.
Eric, clear?
Yeah, for me it's clear.
Very good. So now, you see, I want to consider the fraction n over b to the power n. So as for the numerator, it's good. We have n. As for the denominator, I rewrite my denominator b to the power n as 1 plus b minus 1 and all this to the power n. Same thing, but now b, first of all, b is greater than 1. You see, b is mth root of a is greater than 1, then b is greater than 1. Then here in the denominator, I want to use my binomial theorem. So n is a natural number, so I write my denominator as this sum 1 plus n multiplied by b minus 1 plus n multiplied by n minus 1 over 2 e minus 1 squared, and so on up to the term b minus 1 to the power n. So now, if you see all the terms in the denominator are positive, are strictly positive. N is a positive number, b is greater than 1, so we have the sum of a number of some positive numbers. So if I keep and only one term in this sum, then you see the denominator is greater. For example, here, what I want to do. My denominator, my sum, which comes from the binomial theorem, is greater than n multiplied by n minus 1 over 2 multiplied by d minus 1 square. Then my fraction can be estimated by 2n over n minus 1 d minus 2 square. Is it clear? So if
Yes, it was clear for me.
it's clear.
For me, yes, but
For-
maybe
for-
for Hussein or maybe somebody else,
Hussein,
it's different.
is it
Yeah, it's clear, Professor. It is clear.
clear?
I'm sorry, my internet.
Thank you.
Mhm.
So now, you see, we can use, as usually, the definition of the limit, because here on the right hand side of this inequality, we have a sequence which converges to 0. In other words, I prefer these words, but if you want, you can rewrite all these in terms of the definition. But in this case, we can also make use of the two policemen theorem. So on the left-hand side, we have a constant sequence 0, and on the right-hand side, we have also a sequence which goes to 0 as n goes to infinity. So in this case, using this two policemen theorem, we have 3.12. Is it clear?
Yes, it's clear.
Good. Now, finally, you see, we have some limits to remember in order to work with the limits without using the definition of the limit, because you see epsilon n or k of epsilon, it's too hard. So we have to use something better in order not to think about this definition of the limit. And in this case, we will use the so-called limit theorem. I think you know this from your lectures, but I will repeat. So attention, please. If I have two sequences, A sub n and B sub n, and I take also capital C as a constant, and I suppose that there exist the limits of the first sequence, A sub n, which is called A, and B sub n, which is called B. You see, attention, here. I repeat, without any notation. If I know that I have two sequences which are convergent, if I have two convergent sequences with the prescribed limits A and B, then we have something, you see? So in order to use this limit theorem, you have to know that you have two sequences, three sequences, four sequences, I don't know how. But any sequence in this case, have to have a limit. You see, a limit, this means that A and B in this theorem have to be real numbers, not infinity or plus infinity or minus infinity, but a real number. Then the limit of A sub n plus B sub n will be A plus B. If I want to consider a sequence capital C multiplied by A sub n, the limit will be C multiplied by A. Finally, multiplication, not finally, excuse me, the third statement. Multiplication formula, if I take the product of two convergent sequences, I will have that the limit will be A times B. Finally, in this case, it is really finally. So the division formula, if in addition we have that all the terms for any n natural, B sub n is not zero and the limit is also different from zero, then we have that the limit of A sub n over B sub n will be A over B. You see, an important moment for you. So if you see in this formula, we say that for any n natural, B sub n is different from zero. You see, if some first terms of your sequence are zero, it is not a problem. We will forget about these terms. It is important that from some natural n, all the terms have to be different from zero. Is it clear?
Yes.
Yes, it is. I think it's pretty straightforward.
So I hope you have all this information from your lecture. So now you turn the page and we will start to consider some exercises. So we will start some ideas how to find the limit. So page 23. You see here, we have an exercise number 12. I want to find the limit as n goes to infinity of x sub n, where x sub n is 5n cubed minus 3n squared divided by n cubed plus 1. You see, whereas in your future work, here you have no problems. You have no problems, really. But in fact, if you turn the page and you consider the division formula, you see that A sub n have to have a limit. B sub n have to have a limit. So in this case, you can see that if I take the numerator of my fraction x sub n, this numerator have a limit which is infinity, plus infinity. Yes. The denominator also have a limit which is plus infinity. So in this case, in mathematics, we usually say that in fact we have indeterminate form infinity over infinity. You see, in this case, the problem is not very difficult because I can rewrite my nth term in the following way. You see, in your practical work, in your homework, also so on. So if you see the fraction of two sequences like this, a rational sequence, if you want, so I have to divide my numerator and my denominator by the largest term. So in this case, you see the largest term is n cubed. So in some, roughly speaking, I want to say that you have to divide your numerator and denominator by n, the greatest power. In this case, it is n cubed. So doing this, I have that x sub n is 5 minus 3 sub n divided by 1 plus 1 over n cubed. So in this case, you see, in this case, if I take this representation of my nth term, I can use my division formula because the limit of the numerator exists and the limit of denominator also exists. Then I write for you in this case, then you can use, it is not an idea, it is only the application of my limit theorem. So the limit of my denominator is the limit of 5 minus the limit of 3 over n. You see, the first sequence is a constant sequence, so it will be 5. As for the second sequence, we use the exercise number 4. So we know that the limit of 3 over n is 0. The same thing we have in the denominator. So you have a constant sequence 1 and the plus the limit of the sequence 1 over n cubed. So the last limit is 0. So the limit of the denominator is 1. So the limit of xn is 5 over 1. That is 5. Is it clear?
Yes, it's clear.
Yes.
Yeah, you see, I hope that for you it is clear, but for other colleagues, I hope it will be better to write at least in this exercise all the details how to use this limit theorem. You see, then we can turn the page. Then we have an exercise number 13. And here x sub n is 9 plus n over n plus 1 in the numerator, and in the denominator we have 2 plus 1 over n. You see, in this case, we can apply our limit theorem directly. Problem, because I know the limit of my numerator, and I know the limit of my denominator. Then, as for the numerator, we have 9 plus 1, and in the denominator we have 2 plus 0. Then the limit of my sequence is 5. I hope it's clear also.
Yes, this one's clear too for me.
Hussein, is it clear?
Yeah, yes, it is. Actually.
LM. Who is LM? LM.
I believe that is Lea. I think that's Lea.
Lea. Mlachnik. Okay. Slovenia. Very good. So now we turn the page. So exercise number 14. So in this case, we have a very simple example, very simple, because x sub n is 3 plus 0.5 to the power n over 0.3 to the power n plus 5. You see, in this case, we can apply our limit theorem directly because we know from the exercise number 6 that the limit of 0.5 to the power n and 0.3 to the power n, these limits are 0. So it is exactly as in the formulation of this exercise number 6. We have the limit of q to the power n, where q is strictly less than 1. So in this case, we have 3 over 5. I hope it is rather clear.
Yeah, I think these examples are rather simple. So, but it's a good way to start learning the theories and stuff like that. But they're clear for me.
It's clear. Very good. So we turn the page and we consider another example, which is also really rather clear. You see, here, it is not a trick, but if you want, I start to forget about the difficulties with some rational fractions. So here I have, you see, I have x over x sub n, which is 2 minus n over n plus 1 plus something like n multiplied by 2 minus n over n plus 2. So you see here, I start to forget about what I call determinate infinity over infinity, because in fact 2 minus n over n plus 1 is indeterminate infinity or minus infinity over infinity. But I start to forget because you have to work with these limits in a rather simple way. So if I take the first fraction, and you see the largest power for this fraction is n to the power 1. So if I divide the numerator and denominator by n, I will have that the limit of the first term is -1. Now let's consider the second term. You see, you have to say, if you are dealing with the limit and if you want to apply your limit theorem, you have to prove that if you have two sequences, the first sequence 2 minus n over n plus 1, and the second sequence n multiplied by 2 to the power minus n over n plus 2. If I write that my limit is the sum of the limit, then I have to say that these two limits exist. In this case, it is very simple. So, as for the first term, if we divide the numerator and denominator by n, which is the largest term in this fraction, you see, you will have -1. Then we also have the second limit. We represent the second fraction as a product of n over 2 to the power n and 1 over n plus 2. So from the exercise number 10, I know that the limit n over 2 to the power n exists, and this limit is 0. The second limit, as n goes to 0, 1 over n plus 2 is also 0. Then we have the sum of two limits, so -1 and 0, and the limit of my sequence x over n is -1. Is it clear?
Yes, sir, it's clear.
Yes, Professor.
Very good. Thank you. So now we turn the page and you see, we have another application of our limit theorem. We want to find, it's a page 27. So we want to find the limit of the sequence x sub n, which is given by n minus 1 over n to the power 5. You see, here, if you want, you have also indeterminate form something like infinity over infinity. But the case is very simple, so I forget about this indeterminate. It is only necessary to rewrite my nth term as a product of five terms. You see, n minus 1 over n is 1 minus 1 over n. I hope it's clear. So we have 5 terms, and due to multiplication of the limits, we have that the limit will be the product of the corresponding limits. Each limit in this equality is 1. So the limit of our sequence x sub n is 1. Is it clear?
Yeah, it's
Yes,
easy
it
to
is.
understand, I guess.
Good. Good. So now it is the next exercise, page 28. So in this case, we are dealing with an indeterminate form like infinity minus infinity. You see why? Because my sequence is defined by x sub n is the first term, n squared plus 1 over 2n plus 1 minus 3n squared plus 1 over 6n plus 1. So if n goes to infinity, the first term goes to infinity. Are you agree?
Yes, I agree.
Really? Agree.
I think so. Yeah, I agree.
Thank you. Then the second term here, it's the same thing, because you see why we say that this term goes to infinity, because in the numerator you have n squared, and in the denominator you have n. So the numerator goes to infinity, I say, faster than the denominator. Faster than the denominator. In this case, you have that the limit of the first term is really infinity, and the same thing we have for the second term. So undeterminate undeterminate form, infinity minus infinity. It is really a usual situation. You will have maybe a number of examples of this on this subject. So how to deal with such an example? So first of all, we go to the common denominator. We go to the common denominator, and I can obtain that the sum of the difference of these two sequences, these two terms, if you want, will be minus 2n squared plus 4n over 12n squared plus 8n plus 1. Even if I say here that we can apply our limit theorem, but you see, in this case, for the moment, we also have the indeterminate form like infinity over infinity. But I do not recall this for you, because you know how to deal with such a fraction. So we have to divide the numerator and the denominator by n squared. The largest term here. So in this case, I will have the limit of minus 2 plus 4 over n divided by 12 plus 8 over n plus 1 over n squared. So my division formula works because I know the limit of the numerator and I know the limit of my denominator. So in this case, the limit of the numerator will be -2. The limit of my denominator will be 12. So the result will be -1/6. Is it clear?
Yes, it's clear.
Good. So now, we turn the page and let's try to discuss another exercise. So I take, you see in this exercise, I take a sequence x sub n, which is different from 1, but the limit of this sequence is 1. Who knows the example of such a sequence? To your mind. The example. Who knows? Eric.
Can you repeat again the
So
numbers that you
you
stated
see,
before?
You see. In this exercise, I say, I take a sequence such that for any n, x sub n is different from 1. And the limit of this sequence x sub n is 1. Can you propose an example of such a sequence? What do you think?
Give me a second. Let me think of one. Yeah, let me see. So if x sub n can I go 1, but then the limit of, like you said, limit of x sub n equals 1. So how can I say? So it would be kind of like the exercise shows. It would be kind of like of a division sequence, correct?
Oh, what you want? I don't know. Okay, I know, but to your mind, to give an example, it is a very important thing in mathematics.
Yeah. Okay, give me a. So I'm trying to think because so I can't. Let me just. I can't give you an example right now. Let me just try to think of something. Let me just write down something, and I'll be able to try to find more examples.
Eric, I will give you an example, and
Okay.
after this, you can find another example. So the simplest example is 1 plus 1/n.
1 plus 1.
You see, for
Yeah.
any n, xn is not 1. And if I take the limit of this sequence, the limit will be 1. Agree?
Yes.
You saying? Are you agree?
Yeah, I agree.
Thank you. So now, the question is, we want to find the limit of another sequence, y over n, if y over n is given by the formula x sub n minus 1 over x sub n square minus 1. You see, in this case, we have an indeterminate form 0 over 0. You see, if
Mhm.
xn goes to 1, then the numerator goes to 0 and the denominator also goes to 0. So you see, in this case,
Yeah.
in this, if I have, you see, in this case, it's more complicated, but it's really simple. In fact, if I have in the denominator xn squared plus 1, we have no problems. You see,
It'll be different.
you have no problems. So it will be 0 by something, by a number, because the limit of xn square exists, you see. So, but in this case, you have 0 over 0. And in determinate form, it is called in determinate form 0 over 0. You have to know this. Okay? So we have, you see, as for the solution, we have, as usually, we have to simplify. We have to simplify our nth term y sub n. So we represent the denominator as a product as xn minus 1 times xn plus 1. So after this, our y over n, the nth term of my sequence y, is exactly 1 over xn plus 1. Clear?
Yeah, yes, it's clear.
Yeah. Good.
Mono.
It's clear now.
So now, in this case, you see, now we can use our limit theorem in order to have taken into account that the limit of x sub n is 1, we have that the limit of y n is 1 over 2. I hope it is clear.
It was very clear, Professor.
Yes, it's
It's very
clear
clear.
now.
Now, I think we will finish rather after the break, but okay. So we turn the page. We turn the page. Now we have the limit, which is in determinate form like infinity over infinity. So here we have that x n, the nth term of our sequence, is given by 2 to the power n plus 2 plus 3 to the power n plus 3 over 2 to the power n plus 3 to the power n. So you see, in this case, as usually, I cannot apply my limit theorem immediately, so I have to rearrange my nth term of the sequence. To this end, you see, you will use this, maybe you will use this idea because it is rather simple. You have in the numerator 2 to the power n plus 2. So I want to keep y. I want to keep only 2 to the power n, and 2 to the power n plus 2 is 4 multiplied by 2 to the power n. Why I want to keep only 2 to the power n? Because I have exactly the same term in the denominator. So in the numerator, I have only a coefficient in front of this 2 to the power n. And the same thing as for 3 to the power n plus 3. So it will be 27 multiplied by 3 to the power n. And my denominator is exactly as in the initial fraction. So it is 2 to the power n plus 3 to the power n. As usually, I want to divide my numerator and denominator by the largest term. You see, I want to divide by the largest term. So in this case, it will be 3 to the power n. Agree? I agree.
Yes, I agree.
So because if you want, it is stupid to recall this, but 3 to the power n is greater than 2 to the power n.
Yeah.
You see. Very good. So I divide my numerator and denominator by 3 to the power n. So as for the numerator, I have 4 multiplied by 2 over 3 to the power n plus 27, and in the denominator I have 2 over 3 to the power n plus 1. So now I recall you the exercise number 6, where we have the limit of q to the power n when u is less than 1. So 2 over 3 to the power n goes to 0. Then you see I can make use of my limit theorem, and I will have that the limit of my numerator will be 27 and the limit of my denominator will be 1. So the result, so the limit of my sequence x sub n will be 27. So is it clear?
Yeah, these examples have been very clear, very good.
So
Yeah, Professor.
I propose you a break 10 minutes, and then we will finish with the second part of my file. We are working very fast, I think. Okay, so the break, 10 minutes.
Okay, perfect.
All right.